All right, let's finish up some of the material that I wanted to cover today in class, but we didn't have time for. So, where did we stop? We had basically gotten to the point where we were able to come up with a data table that explained the motion of our ball rolling down the inclined plane. Remember, I spaced the dominoes in a way that they would fall in a very even way, so that we could just kind of call the time intervals between each subsequent domino falling. That could be our unit of time. I chose to call it clicks. And here we actually see the distances or the positions of the ball at those times. So that's one of the things, one of the terms that we might be thinking about is position. Position is something that we like to know when we're studying the kinematics of an object. Position is simply where is it? And when you determine the position, you've chosen some sort of point where you say you're measuring in the x direction, or horizontally, you can just say, okay, this is where I'm going to say the position is x equals 0. And in a particular direction, I'm going to measure from that x equals 0 and go from there, where 5 centimeters away from that, 20 centimeters away from that, etc. So position is one of the first things that we would talk about when we're talking about the information we want to know about an object as it's moving. So normally we're going to designate the position by either x as our variable or y. Usually this is when x we use when we're talking about horizontal motion, and y we usually use when we're talking about vertical motion. So, and we saw this as well when we get this information about the ball going down the incline, we were able to make a graph. This graph, to be honest, this should be called position, and it's measured in centimeters. And then the time, which is t, is measured in clicks. And then we could call this graph, the proper name for this would be position versus time. This is always the y-axis, and this is always the x-axis when we're naming the graph of blah versus blah. It's whatever's on the vertical axis versus whatever's on the horizontal axis. And as we said in class, you can see from this picture, because of the shape of the curve, that the ball is traveling further and further between each subsequent click. So we know that it's accelerating, it's speeding up. So what we're going to talk about now are two different definitions. And interestingly, we're going to say that one of the terms that you might be used to using is not one that we use a lot, and then the term we're going to use might not be as familiar. So what the heck am I talking about? So in physics, when we want to see how far an object moved, we're going to be looking at the change in position. And so the change in position, which is delta x here, another name for that is called the displacement. And so when we find the displacement, we literally take the two position values. So right here, the subscripts mean final and initial. So what was the final position minus the initial position? That gives us, that difference gives us the displacement, which is delta x. When we do delta is always going to be final minus initial. That's how it's always found. Now, you might have thought we would be talking and calling that the distance that it's traveled, but in physics, distance is different because displacement is simply the change in the two positions, but it doesn't necessarily talk about what happened in between. It really only talks about like where did it start and where did it end. It doesn't talk about what it did in between those two times. Now, distance is the total length of the path followed. So, for instance, if this is let's say this is our initial position, and this is our final position. the object might have just gone from here to here, but it also might have gone maybe all the way over here and then turned around. And so this is like path 1, and this is path 2. Now, for both of these paths, the displacement will be the same because you have the same initial and final positions. But the distance traveled for path 2 is going to be bigger than the distance traveled for path 1. And so remember that distance is something different. It turns out that we don't usually use distance when we're talking about, when we're doing physics. We usually just use displacement. Another thing that can come up when we find displacement is displacement sometimes will be a negative value. And what does this mean? Well, basically, a negative displacement kind of hints at a movement in a particular direction. So let's say, we're looking at horizontal motion. We're going from left to right. And if I start here and I end here, and this is x equals 0, I'm actually going to my delta x is actually going to be less than 0. And what does this mean? It means that we moved to the left. And if we had a delta x, if a displacement was greater than 0, it would be saying that we have a motion to the right. So bottom line, the positive and negative signs are telling us something about the direction that the object moved, the direction of motion. And that's important. We're going to learn about quantities that we call vectors. And vectors in physics are quantities that have a magnitude and a direction. Now, when we have a displacement, if our displacement is minus 5 meters, the negative sign gives us the direction because it means that we're moving to the left. And the magnitude is the 5. That's like how big it is, how big the displacement is, and the minus sign tells us the direction of it. So the terms that we're describing, like displacement, that's a vector quantity. Now, sometimes there's quantities that only need a magnitude to describe them, and those are called scalars. And so we don't get into vectors in the next chapter that we cover, but just for example of quantities that are vector quantities, which have a direction. Examples would be, of course, displacement, velocity, acceleration. And these are all things that we're going to run into in this chapter, chapter 3. And later on, we'll learn about things like force. That's just another vector that we'll learn about in a later chapter. Scalar quantities only have magnitude. An example of a scalar quantity is time, so they don't have any direction. Speed. Speed is just how fast you're going. It's just the magnitude of velocity. Mass. That's another example of a scalar quantity. And so that's just a really quick introduction to these values. If it's not crystal clear, it's okay because we're going to come back to this many times during the semester. But what we need to know right now is when we're talking about one-dimensional motion, the direction of the motion is going to be given by the sign of the value. And so if we're moving horizontally, usually things that move to the right we say are positive, and things that move to the left are negative. If we're moving in the vertical direction, usually things that go up we say are positive, and things that go down we say are negative. So that's kind of a sign convention we'll be using. Now that we know what displacement is, remember, this is displacement. What we saw with our ball was that the displacement got bigger as time went on. And so we want to talk about how fast things are going. So we're going to first define what we call the average velocity, which is the rate of change of displacement. It's just the displacement over the time. And as you can see, we choose 2 points to find the displacement, and the t, delta t, also means t final minus t initial. So it's also, so these two go together, so it has a particular position at that time, and then it has an initial position at that time. And so those pieces of information go together, and we find the average velocity. Now, we're going to go back to this graph that we looked at with our ball rolling down the incline. And what I did was I chose 3 different average velocities. And they're represented in a way by the red line, the green line, and the blue line, because what we've done is we've chosen different points to compare to calculate the average velocity. So for instance, this one uses the final point and the initial point to find the average velocity. But the green line actually used 2 different points. It used this point and the beginning point. And finally, the blue line found the average velocity between 2 different times. So we always were doing it from the initial time of time equals 0, but notice that the average velocity here really depended on what 2 times you looked at to compare to find the displacement. And so we see that the average velocity, which, notice, remember how we defined the average velocity? This is where the graph, we can get information from the graph. If we actually wanted to do the calculation for the average velocity for these different lines, which has given us 3 different average velocities, what we would be doing would be finding the slope of the line. So for instance, for the red line, I would be looking at here's the run, and here's the rise. And the slope is equal to the rise over the run, which is equal to delta x over delta t. So the slope of that line, that red line, is the average velocity between t equals 0 and t equals 5. The same thing can be said for the other 2 lines, but it would just be a different slope. And that's really helpful. But the other thing that we notice is that the average velocity is very dependent on what time intervals we choose. We can see that it's gradually getting bigger and bigger, which tells us that in a sense the average velocity is a very kind of glossing over all the details. It's just like, well, in the first 5 seconds, this was kind of the average velocity of the object, but we actually can see that the velocity was constantly changing. So is that average velocity a really useful value? And in this case, it really isn't, because of the fact that, as we had noticed in class, that ball is accelerating as it goes down the incline. So what would be a better way to look at this? A better way to look at it would be if we could know the velocity at a very particular time. Instead of saying the average velocity between t equals 0 and t equals 3, what if I said I want to know the velocity at t equals 3? when you're asking for that, you're looking at what we call the instantaneous velocity. Instantaneous velocity is a mouthful, so we'll usually just call it velocity. The definition of instantaneous velocity is that it's the displacement over the time interval, but we're allowing that time interval to go to 0, which makes it the derivative of the position with respect to time. So this is a derivative. How we find the instantaneous velocity on a graph, remember the slope of the line joining the 2 points. This is the average velocity, the slope. But what we want to do in order to find the instantaneous velocity is we draw a tangent to our curve of position versus time and find the slope of that tangent. So this is what I did here is I drew a line that was tangent at t equals 1 second. So if we found the slope of that line, that would actually be the instantaneous velocity of that ball at t equals 1 second. So this is just some definitions, and what we're going to do in class on Thursday is we're going to start to try to apply this information.